This picture has been traced from the preceding picture, so it's a fairly good representation of the circular model. I've just labeled two angles, two positions on the arc of the circle, the pi over 6 or 30-degree position. And okay, if we label the circle in this direction, then this direction is going to be negative, so I can say that this is negative pi over 6 or negative 30 degrees. Starting from here, the positive direction is counterclockwise, so here's 30 degrees. Starting from here, the positive direction is again counterclockwise, but we're moving in the clockwise direction, so that direction is going to be designated negative. Now, the angle could also be, this position on the circle could also be labeled as we move around in this direction, and that would be 11 pi over 12 or 330 degrees. We say that the angle negative pi over 6, negative 30 degrees is coterminal with positive 11 pi over 6 or 330 degrees, meaning that we end up at the same point. We terminate at the same point, whether we go negative 30 degrees or positive 330 degrees. Okay, now I'm going to construct a triangle. I'm going to go from the origin out to the pi over 6 position, and then from the origin to the negative pi over 6 position, and from the pi over 6 position straight down to the negative pi over 6 position. Now again, remember, this is all based on hand-sketched lines on a circle. None of these angles were measured precisely, so there could be some errors here, but we understand that this represents a triangle whose angle here is 30 degrees and whose angle here is 30 degrees. Also, it should be obvious from the symmetry that we would have in the ideal object that these two angles have to be equal. Now, since we know that the three angles of a triangle add up to 180 degrees, these two add up to 60 degrees, which means that these two have to add up to the other 120, which means each of these is going to be 60 degrees. And I label that as 60 degrees rather than pi over 6 radians, but I'll label in terms of radians as well. Now, that gives us a triangle, all three of whose angles are the same. Now, if all three of the angles of a triangle are the same, then we call that an equilateral triangle. Now, I'm just going to hand sketch a triangle here to approximate our equilateral triangle. I don't know how well I did. I think I've got this angle a little too big because these look a little smaller. If I'd done this right, then if this triangle was rotated when you weren't looking, it would look exactly the same. If you rotated 120 degrees, it would look exactly the same as if it was in this position. And if we rotated the other direction 120 degrees, it would look the same. Okay, anyhow, this is going to represent an equilateral triangle. Now, this circle is assumed to be a circle of radius 1, a unit circle. So that this distance here, the length of this line is 1, and the length of this line is 1. So we know that the length of this line should be 1, and the length of this line should be 1. And by the symmetry and so forth, we conclude that the length of this line should also be 1. This one looks a little long to me, but that's just because of the way I drew it. We're going to pretend it's correct. If I cut this in half, then I have two triangles here, one of which has 30 degrees here. We still have our 60 degrees here, and this is, of course, a right angle, 90 degrees. And we have the same thing down here. We have 30 degrees, 60 degrees here, and 90 degrees here. We take just one of those triangles, either one, but I'm going to take the upper half. Okay, I'm going to draw it a little bigger. Just draw it to a slightly bigger scale. Okay, so if this is 30 degrees and this is 1, and if this is half of this triangle, then what can we say about the other two sides? Well, we don't really know what to say about this side, but one thing we can certainly say about this side is since these two triangles are the same, each of these has to be 1/2. This is 1, so here's 1/2 and here's 1/2, so that this side is 1/2. Now another thing, and we also know this is a right angle, another thing we know about right angles or right triangles is that if we have any right triangle, and I'm not even trying to draw this one the same as the other one, but if this is a right angle and this side is A and this side is B and this side is C, then we know that A squared plus B squared equals C squared. And it follows then that if we know, say, B and C, which is what we know down here, we know the angle of the shorter, let's back up a second. We know that the C is the long side of the triangle. That's the side that's opposite the right angle. So that 1 is the C side of this triangle because it's opposite from the right angle. So for this triangle, C equals 1. And just going with the labeling we have here, we're going to say that B equals 1/2. What do we conclude? Well, first of all, A squared plus B squared equals C squared, so that A squared must equal C squared minus B squared. If you add two numbers to get a third one, then if you subtract the second of those numbers from the third, you get the first. Okay, so A squared is C squared minus B squared. So that A is the square root of C squared minus B squared. In this case, remember that C is 1 and B is 1/2, so that our side A, our unknown side, is the square root of C squared, which is 1 squared, minus B squared, which is 1/2 squared. Well, let's see now. 1 squared is 1. 1/2 squared, 1/2 times 1/2 is 1/4. So this equals the square root of 3/4. Now, the square root of 3/4, by the properties of square roots, is the square root of 3 divided by the square root of 4. The square root of 3 is a number that we might or might not know, but the square root of 4 we certainly know is 2. 2 times 2 is 4, so the square root of 4 is 2. Now, this is, excuse me, the third side of this triangle. Now, the third side of the triangle is from here to here, so that from here to here the distance is the square root of 3 over 2. Well, this is the 0 point of the x-axis, so the coordinate of this point must be at x equals square root of 3 over 2. That point right there is at x equals square root of 3 over 2, and since the cosine of pi over 6 is that x coordinate, we conclude that the cosine of pi over 6 is the square root of 3 over 2. Now that's kind of a neat thing. We can approximate the square root of 3 but we can only approximate it. The square root of 3 is approximately 1.732, but there are a lot of numbers after this too, an infinite string of numbers, non-repeating, non-terminating. Okay, this square root of 3 is an irrational number. It never ends. You can never pin it down precisely. However, square root of 3 over 2 is then approximately 1.732 divided by 2, and that's not difficult to divide out, and what you get here is 0.866. Now remember that before previous estimate was that the cosine of pi over 6 was about equal to 0.9. Well, that's consistent with what we got here. If we round off 0.866 to the nearest tenth, we do get 0.9, don't we? So, and as we said before, it looked like it was between 0.8 and 0.9. We couldn't tell exactly where, but just by hand-drawn sketch, we could tell that 0.9 was a reasonable estimate. Now we've used a symmetry argument and the Pythagorean theorem to find out exactly what that number should have been. It should have been exactly square root of 3 over 2. 0.866 is not an exact result. It's an approximate result. Remember, there are numbers after the 2, an infinite string of numbers after the 2 in the 1.732. That's going to give us an infinite string of numbers after the 6. However, we do know that to 3 significant figures, the cosine of pi over 6 is 0.866. We compare that with our previous estimate, and we remember that the cosine of pi over 6 is known exactly to be square root of 3 over 2. This is exact, this is approximate, and this was our first approximation.